Today, many different polymers are used in aircraft and space shuttles. We're going to have a look at a few of them. But first, you might be asking, what's a polymer? A polymer is a large molecule made by connecting many small repeat units, which are called monomers, together by a process called polymerization. We make these molecules easier to look at by abbreviating their structures. The section that's being repeated we call the repeat unit. We then put this in brackets and subscript the number of times it has been repeated. From this, we can tell how many there are in the full structure. Polymers have a wide range of properties. Some are flexible, strong, light, or heat-proof. Because of this, they have many applications. For example, polyethylene is used to make plastic bags, cling film, and even in some joint replacements. Kevlar in bulletproof vests and nylon in clothing are also polymers. They are the most used compounds in the world. The first polymer we're going to look at that is used in airplanes and space shuttles is called tauron polyamide imide. It can withstand high temperatures up to 275 degrees Celsius because of the amide and ether functional groups. It's very strong due to the aromatic rings in imide functional groups. Also, it is flame resistant, hard wearing, resistant to strong acids, and is an excellent adhesive to carbon, glass, and metal. It is used in many roles in space and aviation, from gears, bushings, washers, and slides to fasteners and seats. This is because it is heat resistant, strong, non-corrosive, and self-lubricating. Manufacturers are replacing the traditionally metal parts of planes with these plastic parts because they are lightweight. This helps to reduce fuel consumptions and hence operating costs. Aircraft interiors, for example furnishings, are often polymers nowadays. The foam in aircraft seats may be Solif 80,000 expanded PVDF. It is incredibly lightweight, ranging from 110 grams per litre to 140 grams per litre, depending on the grade. It is fire resistant, chemical resistant, and UV resistant. Radol polyphenol sulfone, or PPSU, is another used for aircraft interiors and airline catering trolleys. This is also used for dental and surgical instruments because it can withstand over 1,000 cycles of steam sterilization without any significant loss of properties. It can also withstand continuous exposure to moisture and high temperatures and still not crack or break when a tremendous force is applied to it. In aerospace, shuttles have to be able to withstand the heat and cold of space while on orbit. To achieve this, a number of different tiles are used, made of different materials, and are placed in different locations depending on the amount of heat protection needed. High temperature reusable surface insulation, HRSI, is used on the orbital underside and made of coated silica ceramics where the re-entry temperature is below 1260 degrees Celsius. The re-entry temperature is the temperature when the shuttle re-enters the Earth's atmosphere from outer space. The HRSI tiles are made of a low-density, high-purity silica amorphous fibre insulation. This means that the fibres are made from sand and are about 1 to 2 mm thick. Because 90% of the tile is air, they weigh about 9 pounds per cubic foot, which is about 144 kilograms per cubic metre. The tiles are thicker at the front of the shuttle, where the re-entry temperature would be higher. They are coated in a mixture of tetrasilicide and borosilicate glass and a few other materials, and then with a silicone resin to ensure that they are waterproof. Low temperature reusable surface insulation, LRSI, is generally used on the front half of the shuttle. These white tiles are manufactured in the same manner as HRSI tiles, but they have a different coating of silica compounds with shiny aluminium oxide. They are white to help manage heat when the shuttle is exposed to direct sunlight while it's on orbit. Felt reusable surface insulation, FRSI, is used where temperatures stay below 371 degrees Celsius. This portion is of the middle of the shuttle, sides, and the upper wing generally. FRSI is a white flexible fabric and gives heat protection up to 371 degrees Celsius. But why is all this needed? It's because the orbiter's aluminium structure cannot withstand temperatures over 175 degrees Celsius without structural failure. The aerodynamic heating during re-entry would push the temperature well above this level in areas, so an effective insulator is needed to protect the shuttle. Where will this technology lead to in the future? Today's technology is pushing boundaries further towards these living materials. This could lead to self-healing, self-sensing, and self-moulding alloys. Wings which could feel changes in pressure or temperature, or transform from liquid to solid when a magnetic or electric field is applied to them, or could unfurl, bend, and shape themselves while flying, are being looked into. Dan Goldwyn, NASA's former administrator, said, "The seemingly effortless flight of birds provides inspiration for new aircraft utilizing wings that reconfigure in flight." The ability to modify wing shape could also be beneficial to the military. Previously, theoretical designs have been significantly restricted by the weight required to bring in the new changeable wings. However, developments in nanotechnology and nanocomposite materials allow the construction of low-weight materials. Could this be the door-opening technology needed to make reconfigurable smart components that could ultimately revolutionize the entire concept of flying?